Hello everybody. In this video we are going to solve dy dx is equal to sine of 4x plus 6y. This differential equation looks like separable differential equation at the beginning, but because we have x and y variable in the angle, it is not separable differential equation. So we are going to apply some different technique. Let t be equal to this angle, 4x plus 6y. And now we can differentiate both sides implicitly. Derivative of t with respect to x is dt dx. Derivative of 4x is 4, and derivative of 6y is 6 dy dx. Again, we are differentiating implicitly with respect to x. Now here we can solve for dy dx. So dy dx is equal to subtract 4 on both sides, so dt dx minus 4, and divide everything by 6, so 1 over 6, 4 over 6. Now let's rewrite better. Dy dx is equal to 1 over 6 dt dx minus, if you simplify this fraction, you get 2/3. Now our dy dx in the original problem is equal to this expression here. Now we can place it with 1 over 6 dt dx minus 2 over 3. So instead of dy dx, I am writing 1 over 6 dt dx minus 2/3 equals to sine of, instead of 4x plus 6y, we have t. Now this looks like more separable differential equation. Let's rearrange a little bit more. Let's multiply everything by 6. 6 times 1/6 dt dx is just dt dx. 6 times this fraction is 4. And 6 times sine t is 6 sine t. Now we can add 4 on both sides. 6 sine t plus 4. Now this is separable differential equation. Multiply both sides by dx. And divide by 6 sine t plus 4. So you get dt over 6 sine t plus 4 is equal to dx. Now this is totally isolated and ready to integrate. So let's integrate left hand side and right hand side. Integral of dx is easy. This is 1 times dx. So integral of 1 with respect to x is x. So this is x plus c. Now we need to work on the integration of left hand side here. For this integration, we are going to utilize double angle identity for sine x. So we know that double angle identity for sine 2x is 2 sine x cosine x. But we are not going to use this form. We are going to use the form of sine of 2x is equal to 2 tangent x over 1 plus tangent squared of x. You need to keep this in your identity bank for double angle identity, because it's very useful in such kind of integration. I'm going to show mini proof of why this identity is equal to that. So we said that sine of 2x is equal to 2 tangent x over 1 plus tangent squared of x. We can rewrite tangent x as sine over cosine using the reciprocal identities. And using Pythagorean identity, we can rewrite 1 plus tangent squared of x as secant squared of x. And we can convert secant squared of x as 1 over cosine squared of x. Again, 1 over cosine is secant x. So 1 over cosine squared of x is secant squared of x. So we're going to replace this with 1 over cosine squared of x. Now what we have is 2 sine x over cosine x over, instead of secant squared of x, 1 over cosine squared of x. Now we have a complex fraction here that we can simplify. So we have 2 sine x cosine x, keep change flip, keep the first fraction, change to multiplication, flip the second fraction. 1 factor of cosine cancels cosine x. So we ended up with 2 sine x cosine x, which was equal to left hand side, which is sine of 2x, which is our double angle identity. So that proves that we can also use this form of sine of 2x. But we don't have here sine of 2t, we have just sine of t. So what we're going to do is we're going to halve the angle here. So we're going to have, if this is sine of x, then we have 2 tangent of x over 2 and 1 plus tangent squared of x over 2. Here angle is double. Here angle is the half of this angle. So x, half of x is x over 2. Now we're going to place sine of t with this, but we're going to use t variable. Let's rewrite. We have integral dt over 6 times 2 tangent t over 2 over 1 plus tangent squared of t over 2. And we have plus 4 here. We don't worry about the right hand side. Right hand side is equal to x plus c, that we can use in the end. Now we're going to multiply all terms on top and bottom by 1 plus tangent squared of t over 2, so we can get rid of the denominator here. Let's do that. 1 plus tangent squared of t over 2 multiplied by top is itself, because we have 1 times dt. So let's rewrite it. I would like to write in red. 1 plus tangent squared of t over 2. We have 6 times 2 tangent t over 2 over 1 plus tangent squared of t over 2 multiplied by 1 plus tangent squared of t over 2 plus we have 4, and we need to multiply that term by 1 plus tangent squared of t over 2 as well. Now denominator cancels with 1 plus tangent squared of t over 2. Now let's rearrange. We have 1 plus tangent squared of t over 2, that we can also replace this with secant squared of t over 2 using Pythagorean identity. So we have secant squared of t over 2 divided by, let's multiply 6 by 2, so 12 tangent t over 2 plus, let's distribute this 4, so 4 times 1 is 4, and 4 times tangent squared of t over 2 is 4 tangent squared of t over 2. And we have dt here. Now we see a quadratic function in the denominator that we can rearrange. Let's rearrange that quadratic function. The pattern is the quadratic denominator that we will be doing completing the square technique. So we have secant squared of t over 2. Now we can also factor out 4 and do from highest to the lowest order. So factor out 4, tangent squared of t over 2. And if I factor out 4 from 12, I get 3 tangent t over 2, and then I get 1 if I factor out 4 from here, dt. So what we did from this step to that step is we ordered this quadratic function from highest to the lowest order and factored out 4. Now we can pull out this 4 in front of integral sign. This is in the denominator, so it's going to be 1 over 4. We have secant squared of t over 2, and then we have tangent squared of t over 2 plus 3 tangent t over 2 plus 1 dt. Now we're going to apply completing the square technique. If you did not solve any completing the square technique in the integration, you should do some practice on completing the square techniques so you can recognize the pattern. Now we're going to complete this. Let's do the side work here. Tangent squared of t over 2 plus 3 tangent t over 2. By completing the square, we take the half of the coefficient of the middle term. Half of 3 is 3 over 2, and if you square it, you get 9 over 4. So we add 9 over 4 plus we have 1 here and minus 9 over 4. So we added 9 over 4 and subtracted 9 over 4. So we did not change this function. Now we have here perfect square trinomial that we can factor out easily. So it's going to be tangent t over 2 plus 3 over 2, the quantity squared, because this is a perfect square trinomial. If you multiply tangent t over 2 plus 3 over 2 by itself, you get this perfect square trinomial. So plus 1 minus 9 over 4. You can express 1 as 4 over 4. 4 over 4 minus 9 over 4 is negative 5 over 4. Now we're going to copy this here in our denominator. So 1 over 4 integral secant squared of t over 2. We have tangent t over 2 minus plus 3 over 2, the quantity squared, minus 5 over 4 dt. Now let's express 5 over 4 as a squared number, so we can apply some other integration techniques. So square root of 5 is square root of 5. Square root of 4 is 2. So radical 5 over 2 squared is equal to 5 over 4. So we have some squared number and some squared number here. Now let's refine this integral a little bit more. We have secant squared of t over 2 in the numerator, and we have tangent t over 2. The relation between tangent and secant squared is derivative of tangent is secant squared. So we can apply u substitution here. Here let's refine a little bit more this integral. We have tangent and secant squared. So the relation between tangent and secant squared is derivative of tangent is secant squared, so we can apply u substitution here. Let u be equal to tangent of t over 2. Then du will be secant squared of t over 2 multiplied by 1/2 using the chain rule dt. Here, if you multiply by 2, so 2 du is equal to secant squared of t over 2 dt. And if you solve for dt here, because we're going to place here, dt is equal to divide by secant squared of t over 2, so 2 du divided by secant squared of t over 2. Now let's replace everything in terms of u. We have 1/4 in front of integral sign. Instead of, let's rewrite secant squared of t over 2. Instead of tangent t over 2, we have u plus 3 over 2, the quantity squared, minus radical 5 over 2, the quantity squared. And instead of dt, we have 2 du secant squared of t over 2. Numerator cancels. 1 is left here, 1 is left here. And we can pull this 2 in front of integral sign. So we have 1/2 here. Let's rewrite. So we have 1/2 integral of 1 over u plus 3 over 2, the quantity squared, minus radical 5 over 2, the quantity squared, du. Now, one final thing to know about this integration is we have elementary integrals that you need to know. This template integral. Integral of 1 over x squared minus a squared is equal to 1 over 2 times a logarithm absolute value x minus a, x plus a, plus c. I'm not going to show the proof of this because this is our elementary integral template that you can now memorize. I can show the proof later in my another video. Here in our case, our x term is like u plus 3 over 2, the quantity squared, and our a term is radical 5 over 2. So we can place this with our template integral. So it's going to be 1/2 times 1 over 2 times a. Instead of a, we have radical 5 over 2 logarithm x minus a. Our x term is, we can bring u back. U was tangent of t over 2. So tangent t over 2 plus 3 over 2 instead of u plus 3 over 2 minus a. Our a term is radical 5 over 2. And we have x plus a. Let me show the formula here. Let me copy the formula so we can directly see. So x minus a, now x plus a. Our x term is u plus 3 over 2 and u is tangent t over 2 from our u substitution. Tangent t over 2 plus 3 over 2 and x part is done. Now plus a. Okay, now if you need to rearrange, simplify, 2 cancels 2, 1/2 times 2 radical 5 logarithm. So 3 over 2 minus this is 3 minus radical 5 over 2. you can leave in this form or you can leave in that form, over tangent t over 2 plus, this is 3 plus radical 5 over 2 plus c. And if you don't like radical in the denominator here, you can rationalize by multiplying radical 5. So this was our left hand side, so we don't keep c part here. Our right hand side was equal to x plus c. So you can leave your answer in this form for that differential equation.